let's try this quick overview again. I say quick, nothing ever seems to be too quick, but yeah, I screwed it up the first time, so here we go. So we're looking at differential equations, and again, this is sort of just this idea that, you know, much of the first page of that quiz is it's just stuff we already knew, really. Well, first, let's see, 1, 2. Now I'm going to skip 3 for the moment. 4, and really even number 5. So you know, 4 of the first 5 questions are all really just based on what the heck is a differential equation. And you know, let's look at something like y equals e to the 2x. You know, so there's a function, and we all know how to take its derivative. If we take the derivative, we've got y prime equals 2e to the 2x. And so that is a differential equation because it relates the derivative, or a derivative, one of the derivatives, first, second, third, and so on, a derivative of a function to another function. And so we have this this y prime equals 2e to the 2x, and if I were to ask you to solve this, well, you know, you could integrate both sides, you know, if I didn't show you the original solution, but if you were given this back in Calculus 1, you know, you'd be just told, well, y prime is 2e to the 2x, what's the antiderivative, right? And in essence, you are, in terms of our differential equations, you are integrating both sides with respect to x. Okay, so we do that, and on the left side, well, one, we could go with just the fundamental theorem of calculus that says, hey, if I have a function of x, it's and looking at its derivative, then this symbol here, this s-looking curve with the dx, if that's the independent variable, then the answer to this is y by our fundamental theorem of calculus and definition as to what this symbol is. Yeah, actually I kind of misspeak there with the fundamental theorem of calculus. That's really with definite integrals. There is the function form where you can think of it as an antiderivative. But really, right, this symbology here on the left is just saying I want the antiderivative of y prime, but we know that's y plus an arbitrary constant. And so I could do it that way. Another way I could do it is by substitution and say, well, you know, dy is y prime dx. Okay, again, that's a definition of differentials. Dy is y prime dx, and so on this side I would have my dy, and on this side I could do a u substitution, something like that, and I would have, you know, e to the u du, where u is 2x, and, you know, I would get my y equals e to the u plus a constant, which is e to the 2x plus a constant. So I can integrate both sides and see that I get it. But typically, you know, something like this, the other thing we can notice is instead of writing the differential equation explicitly like this in x, where I can just quickly do an antiderivative, we'll notice y is e to the 2x, so that's actually y there. And so it could be that you were given, say, something like this, y prime equals 2y. And in which case, well, it's not so obvious how to solve that, but I could still check the solution, because what I can do is I can take my y prime, you know, so somebody tells me e to the 2x is a solution to this, well, what can I do? Well, plug it in. On the right-hand side, 2e to the 2x. There I just plugged in y. And on this side, I just plug in my y prime. And that I found was 2e to the 2x. And lo and behold, yep, they are equal. And so, you know, that's one aspect of differential equations is these are just quantities that if I'm given enough information, like a possible solution, I can always check it simply by plugging everything in. I plug in the derivative, I plug in the function itself. If I had x's here and maybe at a particular point or something like that, I just plug in what I have. And that's no different than algebraic equations, and it's just this matter of knowing what these things mean. And so I see this y prime equals 2y. Well, y is a function of x. If you tell me what that is, I can plug it in. Y prime is a function of x. If you tell me either what y prime is in terms of x, or you tell me what y is in terms of x, I can find that derivative and plug it in and check. So I can always do that. Then, you know, let's look at this. We have something that looks, and I'm only going to look at x greater than or equal to 0. Here's 2, and e to the 2x heads up like that. Well, you know, suppose I want to go here to some x0, and there's y0, and I want the tangent line. Well, the tangent line, we know, again, this is a Calc 1 thing. I know the tangent line is y equals, and I'm just using the point slope form, so it's y prime at x0, because that's the slope of the tangent line, y prime at x0 at that point. And then times x minus x0, so this is our point slope form, and plus y0. So there's the tangent line. And if I wanted to go up here, if I wanted to go up, say, h units to x0 plus h and evaluate the function up there, got a little messy, but if I wanted to evaluate the function up there, well, you know, again, one of the things we did in Calc 1 was we said, well, you know, we could approximate that using the tangent line. So I could get this new point here. It would not be, whoops, sorry. You know, here's the y that we actually want. But, you know, I'm going to be a little below that. And, you know, so there's some y hat, say. My y hat approximation is going to be my y prime at x0. Plug in x0 plus h, my new x value, x0 plus h minus x0 plus y0, and that reduces to y0, or y prime of x0 times, well, x0 is canceled, times h plus y0. So there's my approximation. Y hat is just that. Well, when you look at Euler's method, that's all it ever does. It never does any more than that. It simply says, remember, you know, we would start with some x0, y0. We would be given what those were. And, you know, I don't know. Let's go with, say, x0 is 1. Y0 then would be e to the 2. And then what you filled in, right, was y prime at x0. You needed to come up with that. Well, y prime at x0 was 2y, so that's 2e to the 2. And then you took that y prime x0 times your step size, h. Suppose our step size is 0.1. So we would have 2e to the 2 times 0.1. But you see, that's just that part. And then what did we do? Well, if I wanted to look at then x0 at 1.1, instead of my actual, or not x0, and get rid of the subscripts, I guess. X and y, 1 and e to the 2, then if I want to get 1.1, I would take my original e to the 2 plus that much. So 2e to the 2 times 0.1. And, well, you know, that's 0.2. I could factor out the e to the 2, and it'd be 1.2 times e to the 2. And that would be a number. But you see, once I've done that, and again, all I did was I used my tangent line formula. I mean, there is the formula to the tangent line always. And so I just took that step size, 0.1, figured out the derivative. Well, you know, how did I get that derivative? Well, I just went back to my derivative there, 2e to the 2x, and so x was 1, so I had my 2e to the 2. I just do that. It's just a tangent line, and so if I know what a tangent line is, and I know that that differential equation is just giving me that slope for any x0, y0, Euler's method is just no big deal. I just keep computing a new tangent line value from my latest values. And so that's what you want to get squared away. If you're having trouble with Euler's method, most likely you have one of two possible problems, maybe both. You know, you aren't really realizing, you have not internalized the fact that that differential equation is simply telling you the slope of y at a particular x and y. Okay, now y is not involved in this equation, but x is not involved in that equation, but they're still both the same equation. So, you know, they are both telling me something about the slope of y at a given x or y, x and y value, and so that's one possibility. You're just not internalizing what you're looking at when you look at a differential equation. It is not real deep. If it just involves y prime, then all I'm doing is I'm talking about some relationship between a function's slope and its position, x and y value. If I start tossing in more derivatives, oh, well then I'm also talking about relationships with concavity and various things like that. So we, you know, that's all you're doing with Euler's method. So make sure you get this idea of what a tangent line is and what the heck a differential equation is saying. And I don't mean, you know, can you interpret it as, I don't know, cows burping in a field? I mean, if you look at a differential equation, do you realize it is simply giving you a relationship between a function's slope and the function position? Okay, it's xy coordinates. And that is all it's telling you. And that may be a very simple relationship, or it may be a very complicated one, but that's all it ever tells you. It just says, hey, this is the slope at this position. And so, in terms of that, we can talk about the slope fields. And so, if that's all the differential equation is doing, well then, when I go to do a slope field here, then what I know is at, for instance, 1 and e to the 2, that slope is 2e to the 2. Now, e is 2.718 and so forth, so e to the 2, that thing squared, that's, I don't know, somewhere around 7 or 8, and then times 2 is 14. That's a very steep slope by that time, but at that point I know that I have a very steep slope. I didn't draw it very well here. I mean, it doesn't look like it's that steep here, but this is the same picture. If that's a 1, and that's an e to the 2, if I were to, oh, well, that was, sorry, e to the 2, there, that is a 2. So that point and that big long tangent line, well, all I've done here is I've made a shorter tangent line, and I can do that at every single point I want. You know, I could do it at 0, at 0, 0. Oh, well, I am going to have trouble there. So every single point that works, right? Because can I do that? Oh, but yes, I can actually in this case, right? Because I can plug 0 into either of these. Now, what you notice is we do have a problem if I plug 0 into this. Well, I get out 1. So that's a 0, 1. If I, you know, plug this, according to this, the derivative can never be 0. But according to this, if y is 0, then the derivative could be 0. Well, you know, so if I let y be 0 at the same time x was 0, it would say the derivative is 0, and actually that would be the solution y equals 0. That's a solution part, but it doesn't go along with the rest of the stuff we have here, right? I never gave an initial condition. Okay, so I could even do things, you know, I could even do 0. Now it won't match up with the rest of the stuff, but I can do it. And, you know, I could go out here to 2. You know, I'll get very steep slopes out here. If I come in here to very small numbers, you know, maybe a half or a tenth or something like that, you know, that's where I'll get slopes that aren't so steep. And, you know, but all I'm doing is the same thing I did here, except I'm just drawing a much, much shorter tangent line. And so I just go to here, I evaluate using my relationship between the derivative and either x or my derivative and y, or if I have a more complicated differential equation, it'll have both x and y in it. But I evaluate that slope and I just say, well, if I'm at that point, take that slope, draw the tangent line, and, you know, and I can draw all those tangent lines as I go. But so, you know, that's all a slope field is doing. And once again, if you are having trouble with slope fields, most likely the issue is you are not really realizing what the heck you're looking at when you look at something like y prime equals something involving x and y. Okay, but that's our first order differential equation is just that idea, and so that's saying, oh, our slope for our function y has some relationship between the position, the xy position, and so, okay, that's one problem. We'll get over that. Now, what do I mean by just keep working at it. Work on getting that idea that this is just telling you the slope at a particular position. And that's all the slope field is telling you. It's the graphical representation of this relationship. Or again, the problem goes back to you don't really get what a tangent line is. Okay, we'll work on tangent lines. And then another one had to do with rewriting a differential equation. Well, again, that's kind of, this idea is, well, I could write that differential equation very explicitly in terms of the independent variable up here, or I could write it in terms of the dependent variable. And, once again, this rewriting as different orders, well, it's just realizing that the chain of derivatives. So y double prime is just the derivative of y prime, right? It's y prime prime. And I could always rename those if I wanted to, right? I could say, instead of y prime, I could say, oh, well, let's call y prime v. And that means that y double prime, simply by substituting in here, is v prime. And so I all of a sudden could make that substitution if I had something like 3y double prime plus 4y prime minus 5y equals x squared. Well, I could take this substitution here and I could say, oh, well, that's 3v prime plus 4v. Now, there's nothing I can do with that y, so that's minus 5y equals x squared. But you see, I've just done an algebraic substitution, and there you go. Now, when you look at something like that, somebody says, oh, well, that's all well and good, but what the heck's v? If I don't show you that equation, then I've taken away some information, right? I've taken away that information. But I can give that information back to you. Oh, I can tell you what v is. V is y prime. But now you see I have two differential equations. They both happen to be first order. And so that's that idea of rewriting something is, well, I can always rename, and I can look at new relationships based on that renaming, and I can always do a little algebra to substitute things in. But again, if I don't mention this, if I just write this new equation here, I've taken away information. Somehow something's missing here. I need to let the reader know, or myself know, that, oh, that v does have a relationship to y, and this is that relationship. V equals y prime, but by doing so, I end up with two differential equations. But now, instead of being second order like the original up here, they're now both first order. Okay, so as I said, nothing's actually quick, but there is a little more in depth of trying to tie all of those, or most of those first questions in the first exam back to some very basic Calculus 1 things. This is really Calculus 1, just saying, well, v is y prime, and so v prime is y double prime, or the first derivative of the derivative is the second derivative of the actual function. That's just Calculus 1, and this other stuff up here. It's really just Calculus 1. And so what you want to do is not look at this stuff like it's totally new. It is not totally new. We are really just building, we're extending on things we already knew from way back in Calculus 1, we're recognizing that we can state these relationships, and we have this vocabulary where we can state those relationships a little differently than we used to, and that's going to be helpful because it may be easier to notice this relationship where y prime is 2y than it is to notice this relationship that y prime is 2e to the 2x, or vice versa, something like y equals e to the 2x. It may be much simpler in the end to think about something conceptually as to how its rate of change is related to the function itself. Okay, so that will do it for this video.